Okay, so next we'll have Mary Wootters, who's an assistant professor of computer science and also of electrical engineering at Stanford University. She's interested in theoretical computer science and the theoretical aspects of engineering, especially concerning communication, storage, and data processing. Some topics include error correcting codes, randomized algorithms, dimensionality reduction, and more. Her PhD thesis won the EATCS Distinguished Dissertation Award, as well as the Myers Memorial Prize from the UMich Math Department. And she's won several other awards as well, including an IEEE Information Theory Society James L. Massey Award this year. And also she's a fantastic teacher, winning a teaching award at Stanford, I guess 3 years in a row, it sounds like. So I guess that means it's gonna be a really good presentation.
No pressure, all right.
Okay, so thanks, Mary.
All right. Thanks very much, Jelani, for the generous introduction. Yeah, thanks everyone for coming. Thanks for the invitation. It's such an honor to get to be here today, and I'm really excited to talk to you about coding for storage and computation. But first, I would like to wish a very heartfelt happy birthday to the Simons Institute. I just cannot emphasize enough how important the Simons Institute has been for my own intellectual life and growth over these past 10 years. I was fortunate enough to be in the very first class of Simons Institute Fellows back in 2013. So when I was still a graduate student. And since then, I've had the opportunity to come back many times. And yeah, every time I come, I encounter new ideas, I form new collaborations. I get whole new research agendas. I think I'd be in a very different place right now, certainly intellectually and probably also personally, if not for the Simons Institute. So thank you very much to the Simons Institute. Thank you to those who've made it possible for these past 10 years. Yeah, and here's to another 10 years. Yeah. The time it took me to do that PowerPoint animation is a testament to my devotion to the Science Institute. Okay, so what am I actually going to talk about today? So this is actually a pretty difficult talk to write. So I was asked to speak about coding theory generally, and I figured that such a talk in this venue should probably check at least 3 boxes. So first, I should probably touch on and celebrate a decade of coding theory at the Simons Institute. Second, I guess I should talk about some of my own work because I'm giving the talk. And third, I wanted to give a sense of what's exciting in coding theory right now and sort of what are some interesting future directions. And so this is challenging because there's a lot of things here, right? So just in this first box, a decade of coding theory at the Simons Institute, it's been a very exciting decade in coding theory. These are just a few things that I could come up with until I ran out of room on the slide. And a lot of these have happened at the Simons Institute or have been built on things that happened at the Simons Institute. Of course, I had nothing to do with most of these, so let's just pass on the second box there. But in the third box, I do have plenty of visions for the future, both inspired by some of these exciting advances up top and also by emerging technologies. So yeah, I think in a half-hour talk, there's just no way I can do justice to all of this. So instead, I'm going to not. So I'm just going to acknowledge that there's been a very exciting decade of coding theory, and the Simons Institute has played an integral role. But what I'm going to do today is tell a much more narrow story, I think, that I do think checks all 3 boxes, but maybe doesn't quite do justice to all of them, certainly not to the first one. Okay, so the more narrow story that I'm going to tell you about has to do, as you can tell from the title of the talk, with coding for storage and computation. So this story starts, not quite a decade ago at the Simons Institute, but rounding up close enough. So back in 2015, with a question about coding for distributed storage. And also with an answer to that question that I worked on with Venkat Guruswamy back in 2015 at the Simons Institute. So the first part of the talk, I'm going to sort of tell you what that question is and what our answer was. It's going to sort of segue into the second part of the talk, which is some more recent work. So I want to tell you about a piece of work that I did recently with Noah Shetty, who's here, Noah, about coding for computation. And as you'll see when I get there, this work sort of directly arises from the work that we did at the Simons Institute back in 2015. So that'll be the second part of the talk, and then that will sort of segue into the third part of the talk, visions for the future. And I want to talk a little bit about this notion of coding for computation, in particular, computing on top of error-correcting codes. So this is something that I think has been showing up a lot recently, or I think it's been showing up for a while, but maybe I've been noticing it more recently, that I think is a really interesting future direction and maybe deserves more study. Okay, so this is the outline of the talk. So let's get started with the sort of the first bullet point. So distributed storage and a walk down memory lane. Okay, so let's travel back in time to 2015 at the Simons Institute. So it's the boot camp for the information theory semester. And Alex Demakis is giving one of the boot camp talks about coding for modern distributed storage systems 4. So he's at the end of the talk, the open problem slide. And so I was in the audience. And there's an open problem here that really caught my eye. It's that one, but let me write that in a larger font. So what Alex asked was, can one get better repair bandwidth for ReadSolomon codes? Okay, so that's some coding theory jargon. But without the coding theory jargon, essentially what that's asking is, can you do communication efficient polynomial interpolation? So actually, just as an aside, this is a talk about coding theory, but almost all the technical stuff I'm going to talk about is really just stuff about polynomial interpolation. And so even if you're not into coding theory, everyone's into polynomial interpolation, right? So there's got to be something for everybody here. Okay, yeah. So what is this question? I need to define this a little bit more. So here's the setup. So this will be the setup for the entire talk. So pay attention. Yeah. So the idea is we want to store some data in a distributed fashion on n nodes. So we have some data f. It's going to be a vector of length k over some finite field capital F. And think of capital F as being kind of large. And we want to store this data on n different storage nodes. And the catch is that some of the nodes might fail, like that. Right? And our goal is to store this data so that it's so that we don't lose any data if a node fails. So we want to basically add some redundancy. Fortunately, this is exactly what error-correcting codes are for. There's a beautiful classical solution to this problem known as ReadSolomon Codes. So this has been around since the 60s. It's ubiquitous both in theory and in practice, and here's how it works. So we're going to first pick n evaluation points, alpha 1 up through alpha n, in our field f. And then we're going to treat our data as a polynomial. So we'll define a polynomial f of x whose coefficients are sort of these data elements. So it's a polynomial of degree k minus 1. And then we're just going to evaluate this polynomial on all of those points and send all those evaluations off to the different nodes. Right, so far so good. So that's it. That's the scheme. And it turns out that this is a great idea for tolerating failures. This can tolerate the optimal number of failures. So to see why, imagine that, say, n minus k nodes fail. And I claim we haven't lost any data because we still have k nodes remaining, right? And we have this degree k minus 1 polynomial, and we can do polynomial interpolation, right? 2 points determine a line, 3 points determine a quadratic, k points determine a degree k minus 1 polynomial. So here we have k evaluation points. We can do polynomial interpolation, recover all of our data. Life is good. Yeah, so for this reason, ReadSolomon codes are a very popular choice, actually in practice for distributed storage systems. Okay, great. So we can handle this sort of worst case setting, but this really is kind of a worst case setting. So what happens most of the time in data centers is not that everything goes down at once, but rather just like one node goes down at a time. So what happens if just one node fails? So let's say that one over there. So now we would like to set up a replacement node. There it is. And this replacement node should have exactly the same information that was on the failed node. So in this case, it wants f of alpha I, so our polynomial evaluated at this ith evaluation point. And it needs to figure out what that data is by contacting all of the other nodes. So how can we do this? Well, we just saw one way to do it. It can just contact k of the surviving nodes, any k it likes, download the contents of each of them. So that's all of these evaluation points, do the polynomial interpolation, and compute f of alpha I. That's what it wants to do. And that works great. But this seems like it might be a little bit wasteful, right? Essentially what we're doing here is we're downloading enough information to recover all of the data. We're computing just this little bit that we want to keep and throwing away the rest. So it's very natural to ask, can we do better? So the first thing we might try is, okay, maybe we can contact fewer nodes. Right? Instead of contacting k nodes, I'm going to contact like k minus 1. Okay. Can we do this? I'm seeing a chorus of head shakes. Very good. Yeah, we cannot do this. Basically, this is like saying, I'm going to give you 2 points on a parabola. Tell me what the third one is. Right? That third point could be anything, and there's always some parabola that goes through those 3 points. So actually, we learn absolutely nothing about that last evaluation if we only contact k minus 1 nodes. Okay, so we can't do better in this way. And actually, before I saw Alex's talk way back in 2015, I think this is where I thought the story ended. We can't do any better. Too bad that's the price we pay for the wonders of ReadSolomon Codes. But it turns out what Alex's talk taught me back then is actually there is some way that we might hope to do better. And that is by contacting more nodes, but downloading less information from each. So for example, could look something like this. So the model here is that each node gets to do some local computation based on what it's storing and also on the identity of the failed node, and then send some message, whatever it wants, down to the replacement node here. So it could be just like a single bit, could be 5 bits, whatever. And from the information that this node receives, it's supposed to be able to recover the missing evaluation point. So codes that work in this model are called regenerating codes. So these have been around since about 2010. They're introduced by Demakis et al. And regenerating codes are basically just codes that allow you to do this. So they allow for low bandwidth reconstruction of one or maybe just a few failed symbols. Okay, so what do we know about regenerating codes? So remember, we're time traveling now, so it's 2015. So what do we know in 2015? So we know of optimal constructions of regenerating codes, but none of these are ReadSolomon codes. Right? So that is to say, we know of different ways of getting the data, adding redundancy and putting it on those storage nodes that has all of these desirable properties, but they're not gotten sort of by following this recipe of treating your data as a low-degree polynomial and evaluating it at a bunch of points. So that's great, but ReadSolomon codes are sort of actually what are used in practice for distributed storage. They have a number of other sort of desirable properties, and also we just love polynomial interpolation. So it'd be really cool to be able to figure out how to do this for ReadSolomon codes. So just a year ago, in 2015, so in 2014, there was this really cool result by Shangmugam et al. Who sort of give a proof of concept to show that actually you could do this. So I found this quite surprising. So they showed that for specific ReadSolomon codes, so like when n equals 5 or n equals 6, they showed that you can actually do this non-trivially. So they figured out like what are the messages that these nodes have to send, for this n equals 5 code, in order to get some progress here. So I thought this was really surprising and exciting. And Alex's question, so now getting back to this talk, hopefully now we have sort of the context to understand what this means. He was asking basically, can we do this more generally? Like, can you do it for any n? Could you even hope to do it optimally? Like, that would be cool. Once again, this sort of polynomial interpolation version is, can we do sort of low communication, 1-point polynomial interpolation? Right. Okay, so that's the question. It really caught my eye. And so I started working on it at the Simons Institute with Venkat Guruswamy. And okay, spoiler alert, the answer is yes, we can do better. So again, this is joint work with Venkat Guruswamy. And one sort of prototypical parameter regime that our work says you can do better in is the following. So I'm just going to sort of show you a cartoon to give you a flavor of the type of result we can get. So in this cartoon, n, does this pointer work? Can you see that? All right, there we go. N is equal to 2 times k. So we sort of have 2x overhead here. And we're going to be working over a field f of size 2 to the t, which is also equal to n. So that means that these evaluation points, alpha 1 up through alpha n, are just all of the points in the field, and the field has size 2 to the t. Nothing about that is particularly important for the setting, except the fact that it's an extension field. So it needs to be an extension field, but beyond that, this can all sort of generalize. Okay, but in that setting, the picture gets particularly nice, and it looks like this. When we're storing our data as a ReadSolomon code and one node disappears, we can reconstruct it by downloading just 1 bit from all of the surviving nodes. Right? So quantitatively, what does that mean? Okay, so the number of bits that we're downloading total, right? This is sort of the parameter of interest, is n-1, which in this case is roughly 2k. So let's compare that to the naive scheme. So in the naive scheme, we'd contact k nodes and download all the information from each of them. All the information is one whole field symbol that's log of n bits. So that's k log n bits total. So we're basically saving a log factor. And moreover, you can show that 2k bits is optimal even at leading constant 2, at least within certain classes of codes. So yeah, so that was pretty nice. I found this to be quite surprising. Okay, so how does this work? So due to time considerations, I'm not going to actually tell you the scheme, but I am going to tell you sort of the high-level framework for it because it's going to show up again. So here's the basic idea for how this works. So we have our field F, and remember that basically the only important thing about F is that it's an extension field, which means that it's a field of order q to the t for some q. So here we're taking it to be order 2 to the t. And F 2 to the t is a vector space over F2, which means that if it's been a while since algebra, you can just think about it as a bunch of binary vectors of length t. Right? So we have a bunch of binary vectors of length t, and that's sort of our alphabet that we're working with. And we're going to use this linear structure. So the way we make our scheme is the following. So for all I, we're going to define some special subspaces, W1, W2, up to Wn, that have the following properties. So first, the dimension of each Wj is t minus 1. So it has codimension 1 in this t-dimensional space. So it's like a hyperplane, or it's like half of the hypercube, right? And then there'll be another property, which I will read in a moment with the aid of a picture. So here's my picture. So on the x-axis here, I have the evaluation points. On the y-axis, I have the field F. And then here I have these subspaces that we're going to define. So each one of these subspaces is like half of the field. So I've tried to draw this to be like roughly half of the length of the y-axis. Right. Okay, and then this other property that we want from these subspaces is the following. For any polynomial of degree less than k, if alpha of alpha j is in wj for all j not equal to I, that is, if you have some low degree polynomial that passes through all of these blue bars, then it must be the case that at alpha I, that polynomial should be equal to 0. So that's the requirement. So there might be many polynomials that go through these blue blocks here, but all of them need to vanish at alpha I. And I claim that if we can come up with a bunch of such subspaces, then we're done. Okay. So why is that the case? Well, the scheme we're going to use is the following. So each node, remember, each node is just allowed to say 1 bit. And the 1 bit that node is going to send is it the case that what I'm holding, is that in wj or not? So they'll either send yes or no, f of alpha j is in wj, or no, it's not. And I claim that this will be enough to distinguish f of alpha I. So why is that the case? It's basically just linearity. So suppose that f is the right answer. So we're after f of alpha I, and g is the wrong answer. So g of alpha I is different. I want to show you that we're never going to confuse the two. So let's consider the polynomial f minus g. So since f of alpha I is not equal to g of alpha I, then this difference is not going to vanish on alpha I. So it doesn't go through this point. So therefore, by our property, there must be some alpha j so that it doesn't go through the corresponding rectangle. So f minus g of alpha j is not in wj for some j. But then that means that f of alpha j and g of alpha j have sort of different statuses with respect to wj. Right? Either one of them is in and the other one is out, or the other one is out and the one of them is in. If they were both in or both out, then their difference would be in. So they sort of have different statuses, but that's exactly what we wanted. That means that node j would return one answer for f and a different answer for g, and we can distinguish them. So therefore, we won't confuse f of alpha I with any imposter g of alpha I. Right? So then we'll get the right answer. So I've sort of described this in a non-algorithmic way, but you can make this algorithmic just by doing some linear algebra. Okay, so that's sort of the framework. How do we get these subspaces? It's not so hard. It's a very explicit, easy way to describe them. It fits on one hidden slide, but for time, I'm going to skip it. But ask me after in a bunch of like 5 minutes or something. It's not so bad. Okay, but so that was our walk down memory lane. That was back in 2015. What's happened since then? Right. So since then, there's actually been quite a lot of work in this area. So here's a bunch of improvements and extensions to our original work. So sort of very exciting stuff leading sort of all the way up into this year. And the basic punchline of this line of work is that ReadSolomon codes are optimal regenerating codes, not just in that parameter regime that I showed you on the earlier slide, but actually in a whole bunch of parameter regimes and also a whole bunch of extensions of the model, and yeah, in lots of different ways. So this is a very exciting line of work. Additionally, right, this is also a statement about polynomial interpolation, which is just sort of a generally useful thing, shows up all over the place. And these ideas have found applications in other areas as well, for example, in secret sharing and in MPC and secure computation. And yeah, so like I said, this pretty much takes us up to the present. There's a couple of 22s on this slide. And that sort of segues nicely into the second part of the talk, what I wanted to talk about, which is some more recent stuff. And this is joint work with Noah Schutte. And we're going to talk, I'm going to talk about low bandwidth computation on ReadSolomon encoded data. Okay, so the starting point is the same. We have the same picture. We have our data. It's encoded on these end storage nodes using a ReadSolomon code. But now I'm going to switch up the goal a little bit. So our new goal is the following. Suppose we have a class curly f of functions that maps vectors to scalars. So it maps data vectors like this down to elements of f. And what we'd like to do is compute some function of this, some function in this class on our data. So the model is going to be, we have our stored data, possibly some nodes fail, and then some querier shows up who wants to know what is phi of f, right? And so the querier is going to broadcast phi and possibly I, the identity of the failed nodes, to the surviving nodes. They're each going to get to send her a bit or a couple of bits, however much they want, again, based on their own data that they're storing and what they hear from the querier. And from this, the querier is supposed to be able to figure out what is that function. Right? And the goal is that we want to sort of minimize the number of bits that go here. Right? So this is a strict generalization of the problem that we were looking at before. So before, this class of functions was just the class of functions phi sub I, which takes your data and asks, what is the ith evaluation point? Right? But we can ask this question more generally. And maybe I'll give this a definition. Let's call it low bandwidth function evaluation. So the main result in our work is a low bandwidth function evaluation scheme for ReadSolomon codes for linear functions. So that is functions that map our data vector f to an inner product of v times f, again, over some finite field. So here's sort of what our result looks like. This is a simplified version with no failures, because this question is actually even interesting, even if there are no failures, which wasn't the case for the original problem. So suppose we have our data, it's stored on these nodes. Our querier comes up and she wants to know what is the dot product of f, our data, with some query vector v. She's going to broadcast v to the nodes, and each of them are going to recover or send her, again, just one bit. Oh, here, sorry, I forgot to say the assumptions for this little toy picture here are that, once again, f is a field of size 2 to the t and n is equal to 2 to the t. Now n is equal to 4k instead of 2k. But basically the same setup. Each of these nodes can send just a single bit, and this will allow the querier to recover this linear function that she's after. Right. So that's one type of result. Let me just make a few comments about this. So just quantitatively, how much are we downloading? For 4k bits, because there are 4k nodes and 1 bit from each. Let's compare this to the naive schemes. The naive scheme would be the same as before. We're going to contact k nodes, download all the information, reconstruct all of the data, compute the linear function, and then throw the rest away. That takes omega of k log n bits. And the thing I find really interesting about this result is that we need omega of k log n bits to do this, even though there are no failures. Even with no coding, we would need k log n bits to do this. So somehow, encoding with an error correcting code here, a ReadSolomon code, like normally we do this because it helps protect us from errors or protect us from erasures. But here it's actually helping us do computation. Somehow the computation that we've done in doing the encoding is then useful later. We can sort of harness that later to do more efficient computation of these linear functions. I find that to be kind of an interesting phenomenon. And just a note, so as before, at least 2k bits are necessary. So we don't quite have the leading constant anymore. I'm not sure what the right constant is. It's a good question. Okay, so that's sort of the simple result with no failures. We can also prove a more complicated result that does have failures. So this is the cartoon for that. You can allow any set of failed nodes up to just a smidge shy of n minus k. So n minus k would be the maximum number that you could possibly hope to do and get a similar result where this 1 turns into an O of 1, and the constant hiding in the big O depends on how close you are to that n minus k limit. Okay. How am I doing on time? When do I have to stop? 5 minutes? Oh, okay, cool. All right. Yeah, so what's the basic idea for this? Well, fortunately, we've already seen it. This is exactly the same slide that we had before, except I've modified the picture very slightly and changed all of the f of alpha i's to dot product of v and f. Basically, all we were using before in this framework was the linearity on the coefficients of f, like f of alpha I is a linear function of the coefficients of f, and so is this. So same thing holds. So all we need to do is find those subspaces. How do we find them? Okay, it's a little bit harder now. Actually, it's quite a bit harder if you want to do the failures, but for the result without failures, it's actually not so bad. Ask me after, but budget maybe like 20 minutes or something. Cool. Okay, so in the remaining, I guess, 4 minutes that I have left, I want to talk a little bit about visions for the future. In particular, I want to talk about this sort of paradigm of computing on top of error correction, which we were sort of exploring in this work. So I think it's a really natural question. How can we efficiently compute on top of error correction? So actually, this is many natural questions, depending on how we define these various terms. I showed you some particular ways to define it in this talk, but there are plenty of other ways that you could define these things. And these questions, for these various permutations, show up in many different domains. So I want to just bring a particular attention to a couple of cases where they show up where the definition of efficient is low bandwidth, because I've been seeing this a bunch recently. This was also part of the motivation for the work I just described to you. So when efficient means low bandwidth, meaning that we're going to measure the total number of bits that are downloaded here, then yeah, this has shown up in a couple of places. So I already told you about regenerating codes, but another place where this has come up, sort of thinking about more general functional computation, is in homomorphic secret sharing. So there are people in this room who know more about this than I do, but the basic idea here is you want to share a secret, and I'm thinking here about information theoretic secret sharing. So let's say we're doing Shamir scheme or something like that. That's basically just doing exactly the same thing of encoding some data with a ReadSolomon code and sending each party a polynomial evaluation. And then the homomorphic part of homomorphic secret sharing says you want to compute some function of the secret by using a short message from each one of the parties. So this is a very similar notion to what we just talked about. And in fact, our approach does give some kind of homomorphic secret sharing scheme for Shamir's scheme for linear functions. But this is a much broader field. There's a whole lot of really exciting stuff going on and lots of different questions you can ask. And yeah, it's a young field, as you can see. This notion was introduced in 2016. Yeah, a lot of the questions going on here kind of have this flavor of low bandwidth computation on top of error correction, especially with Shamir's scheme. Another area I want to mention is that of coded computation. So in coded computation, the basic idea is you want to do some distributed computation task, like distributed matrix multiplication or distributed gradient descent or something like that. And the idea is that you can add redundancy to your data, so basically encode it within error correcting code before sending it off to the compute nodes in order to speed up your computation in some way. So for example, maybe you want to deal with stragglers, that is compute nodes that might be slow or non-responsive. Or maybe you just want to reduce the communication complexity, as we've already seen. So again, this sort of has a similar flavor. And yeah, and again, our work does have some implications in coded computation, for coded computation of linear functions. But again, it's a very big area, and there's a lot of really exciting work going on, which also sort of has this flavor. Okay, so I'm running out of time, so I'll just say there are a bunch of other questions that have this flavor, some of them even classical. Like once you start thinking about this, like a lot of different questions in coding theory can be shoehorned into this general framework, at least for very specific classes of functions. And sort of getting to this visions of the future, I think that this is a really natural notion. especially the low bandwidth part I've been seeing a lot recently. And I think that sort of this notion of efficient computation on top of error correction is showing up on a lot of places. And it seems like it might be important going forward. And I really think it deserves being studied in kind of a unified way, as opposed to an ad hoc way for lots of different families of functions and lots of slightly different settings from lots of many different communities. I think there's probably a lot to be gained by putting it together. Okay, so I should wrap up. So I just want to have just one more vision of the future, if I may. This is a much more concrete vision. So I'm looking into my my coding theory crystal ball here, and I'm seeing a workshop. Right? Yeah. So at Stock /TheoryFest 2022, in less than a month, I'm going to be co-organizing a workshop on recent advances in coding theory with Noga Ranzui. So it's 3 days during Stock. We have a fantastic lineup of speakers. If you'll be at Stock, please stop by. It's going to be fabulous. And one other thing that I just now recently started seeing in the future of coding theory is a whole Simons program on coding theory, which was just approved. So co-organized with Sibakant Gopi, Venkat Guruswamy, Henry Pfister, and Gilles Zamore, we'll be organizing a Simons Institute program on coding theory in spring 2024. So mark your calendars. Okay, so I'll stop now. Once again, happy birthday to the Simons Institute.
Thank you, Mary. Any questions for Mary? Shafi?
So like your last slide with this idea of, the whole computation on coding, the homomorphic secretarying. So it comes to mind, Daniele's talk when he was talking about this definition of homomorphism, this alternate definition. I don't know if you were here yesterday morning when Daniele spoke about this composing functions rather than the traditional homomorphic. And I was wondering, so suppose you have two pieces of information. It's stored in an error correcting code version, and now you want to do a computation on both of them in that form. Might be an interesting place to look at.
Yeah, that's a really great suggestion. Yeah, and actually, one of the things that I was intending to say on this slide, but I guess I went through it a little quickly, is that I think it would be a great idea to sort of take as a model for how to approach this question, like what happens when you replace error correction with crypto, or like with cryptographic encoding, because that's a question that's been extremely well studied and very, very fruitfully so. I think that's a fantastic suggestion for taking some of those ideas, about composability and stuff and applying it here. I haven't thought about it myself, but yeah, thank you very much. That's really good. Yeah.
Any other questions? Boaz?
So is it correct that often when you use this distributed storage, you're actually storing many code words in parallel? And is there like a chance of amortization or some kind of saving using that?
Yeah, that's a great question. Yeah, so the question is like, typically in actual distributed storage systems, the data is kind of like striped, right? So you're storing lots of different code words in parallel. I think I actually have a picture on a hidden slide somewhere. Maybe not. Oh yeah, there it is. So yeah, so the picture actually looks more like this. And the question is there chance for amortization? So actually, I'm implicitly already using that. You notice that I was always talking about download bandwidth and never about upload bandwidth. And the reason that that's okay kind of is because of this. You can sort of amortize the upload bandwidth away. To get more things. Yeah, so another option for amortization, which applies to our work, is you might have, right, so I was only working over extension fields, but in a lot of cases, it's much nicer to work over prime fields. You can embed the integers there, or for other reasons, you might want to work over prime fields. And if you want to work over a prime field, you can actually use our scheme for that by kind of packing things into an extension field and amortizing and doing a bunch at once. So maybe that's another opportunity for amortization. But yeah, it is a good question. There must be other opportunities that take advantage of that striping. That's a really good question. Yeah.
Okay, let's thank Mary again.